The universe is nearly 14 billion years old. It contains over 2 trillion galaxies. Each galaxy holds hundreds of billions of stars, and around many of those stars, planets orbit quietly in the dark. Statistically, life should be everywhere, and yet, the universe is silent. No signals, no visitors, no undeniable proof that anyone else has ever existed. This contradiction has a name, and it is one of the most unsettling questions humanity has ever asked. If the universe is so vast, if the conditions for life are so common, then where is everyone? This silence is not comforting. It is disturbing, because it forces us to confront a terrifying possibility. What if the universe isn't empty? What if civilizations rise all the time, but something always happens to them? Something that stops them from ever being heard. Something that may still be waiting for us. In this video, you will discover what the Fermi Paradox really is and why it still has no answer. Why advanced civilizations might choose silence instead of communication. The theories that suggest intelligent life destroys itself before spreading the terrifying idea of the Great Filter, and what humanity's future might look like if the silence is a warning, not an accident. Welcome to Where the Light Ends, a place where space grows silent, light fades, and the universe begins to reveal its darkest secrets. For centuries, humanity believed the night sky was simple. Stars were distant lights, fixed in place, circling a universe designed around Earth. That belief collapsed when science revealed a far more unsettling reality. The universe is vast beyond comprehension, ancient beyond imagination, and filled with more worlds than any myth ever dared to suggest. Modern astronomy tells us that there are over 2 trillion galaxies in the observable universe. Each galaxy contains billions or even hundreds of billions of stars. Around many of those stars orbit planets, rocky worlds, gas giants, frozen moons, and ocean-covered spheres drifting silently through space. With this scale alone, one conclusion seems unavoidable. Life should not be rare. It should be common, perhaps even inevitable. And yet when we listen to the universe, we hear nothing. This contradiction lies at the heart of what we now call the Fermi Paradox. It is not a theory, and it is not a speculation about aliens. It is a conflict between what the universe statistically should contain and what we actually observe. Enrico Fermi, a physicist instrumental in the development of nuclear technology, voiced this paradox in 1950 with a simple question: where is everybody? At the time, the question seemed almost casual. Today, it is terrifying. Because the more we learn about the universe, the louder that silence becomes. Why the universe should be full of life. To understand why the Fermi Paradox exists at all, we need to understand how favorable the universe appears to be for life. Life on Earth emerged remarkably early. Almost as soon as the planet cooled and liquid water stabilized, simple organisms appeared. This suggests that life does not require extraordinary conditions, only the right chemistry and enough time. Stars much older than our sun exist throughout the galaxy. Many of them formed billions of years before Earth even existed. If life developed on planets orbiting those stars, intelligent civilizations could have had an enormous head start over humanity. Even a technological advantage of 1 million years would make a civilization effectively godlike by our standards. And with enough time, expansion becomes inevitable. A civilization does not need faster-than-light travel to spread across a galaxy. Even slow-moving probes, traveling at a fraction of light speed, could colonize an entire galaxy in a few million years. On cosmic timescales, that is a blink of an eye. So if intelligent life is common, the Milky Way should already be saturated with evidence of it. But it isn't. In the 1960s, astronomer Frank Drake attempted to formalize this expectation with what became known as the Drake equation. Rather than providing a single answer, the equation breaks the problem into variables. How often stars form, how many have planets, how many of those planets can support life, how often intelligence evolves, how often intelligence develops technology, and how long such civilizations last. While many of these values remain uncertain, modern astronomy has dramatically improved our estimates. We now know that planets are extremely common. Habitable zones are not rare. Organic molecules exist throughout the galaxy. From a purely statistical standpoint, the universe appears biologically generous. And yet, every attempt to detect intelligent signals, radio transmissions, laser pulses, artificial patterns, has failed. SETI has listened for decades. Advanced telescopes scan the sky constantly. The result is always the same: silence. In science, absence is not meaningless. Silence itself becomes information. If civilizations commonly develop technology, then either they do not last long enough to be detected, or they deliberately avoid detection. Both possibilities carry disturbing implications. The first suggests that intelligence contains a built-in self-destruct mechanism. The second implies that remaining hidden is a survival strategy. Neither interpretation paints a hopeful picture. The silence forces us to ask whether intelligence is not a triumph of evolution, but a temporary phase, a brief flare before extinction. What makes the Fermi Paradox so unsettling is that it turns the universe into a mirror. Every proposed explanation reflects something about humanity itself. When we imagine civilizations destroying themselves, we are not imagining aliens. We are extrapolating from our own behavior. In just a few centuries, humanity has created technologies capable of ending civilization. Nuclear weapons, environmental collapse, engineered pathogens, autonomous warfare, and artificial intelligence all represent powers that evolve faster than our ability to control them. If this imbalance between capability and wisdom is universal, then the universe may be filled with short-lived civilizations that burn brightly and vanish quietly. The night sky may be a graveyard. Another disturbing aspect of the paradox is timing. If civilizations are common but short-lived, then the odds of two existing at the same time become very small. Civilizations may rise and fall like sparks in the dark, rarely overlapping long enough to communicate. In that scenario, the universe is not empty. It is simply out of sync. This idea suggests that humanity may already be too late. Other civilizations may have existed billions of years ago and vanished long before Earth developed complex life. Their signals faded, their structures eroded, and their history erased by cosmic time. What remains is silence. At its core, the Fermi Paradox is not asking where aliens are. It is asking how civilizations survive themselves. The universe appears capable of producing intelligence, but not of preserving it. And if that pattern is real, then humanity is not special. We are simply next. The silence may not be a mystery waiting to be solved. It may be a warning. If intelligent civilizations are not being detected, then something must be preventing them from leaving a lasting mark on the universe. This realization shifts the question from astronomy to survival. Instead of asking how often life begins, we are forced to ask how often it endures. One possibility is that intelligence itself is unstable. On Earth, the rise of technological capability has not brought harmony or long-term planning. It has accelerated conflict, resource extraction, and existential risk. If intelligence naturally leads to technologies that outpace ethical development, then collapse may be the default outcome rather than the exception. From this perspective, civilizations do not vanish because of external cosmic disasters, but because of internal pressures they fail to control. The average lifespan of a technological civilization may be far shorter than we assume. Humanity has been capable of radio communication for barely a century. Nuclear weapons have existed for less than 80 years. In that brief window, we have already come dangerously close to self-annihilation multiple times. If other civilizations follow a similar trajectory, the period during which they are detectable may be extremely short. A civilization might emit signals for only a few hundred or a few thousand years before collapsing, transitioning, or going silent. On cosmic timescales, this is almost nothing. In this scenario, the universe is not empty. It is simply quiet most of the time. Another explanation lies in planetary limits. Technological civilizations consume energy at increasing rates. They alter their environments, destabilize climates, and exhaust resources. If growth continues unchecked, ecological collapse becomes inevitable. On Earth, industrial activity has already reshaped the planet's climate in a matter of centuries. If similar patterns occur elsewhere, civilizations may undermine the very conditions that allowed them to emerge. Rather than expanding outward, they may collapse inward. The universe may be filled with worlds that briefly hosted intelligence before becoming uninhabitable. Technology enables survival, but it also amplifies risk. Artificial intelligence, genetic engineering, and autonomous systems introduce failure modes that are difficult to predict or contain. A single misaligned system could destabilize an entire civilization. If advanced civilizations routinely create technologies they cannot fully control, then technological maturity may represent a bottleneck rather than a triumph. The path to the stars may be blocked not by physics, but by design flaws in intelligence itself. This possibility reframes the Fermi Paradox as a problem of engineering ethics rather than cosmic rarity. Some researchers suggest that advanced civilizations may exist but remain invisible. They may abandon noisy radio communication in favor of technologies we cannot detect. They may retreat into digital realities, consume minimal energy, or operate on timescales that make detection difficult. From our perspective, such civilizations would be indistinguishable from absence. Their silence would not signal extinction, but evolution beyond our observational reach. However, this explanation still raises a troubling question. If advanced intelligence tends toward invisibility, then contact may be impossible by design. The early universe was violent. Gamma-ray bursts, supernovae, and unstable stars may have sterilized large regions of space repeatedly. Intelligent life may have emerged many times only to be erased by cosmic catastrophes before it could spread. Even today, certain regions of galaxies may be too dangerous for long-term survival. The Milky Way's structure itself may limit where advanced life can persist. Civilization may require a narrow window of stability that few planets ever experience. If this is true, then Earth may be unusually fortunate or dangerously temporary. Taken together, these explanations suggest a disturbing pattern. Life may be common, intelligence may emerge repeatedly, but long-term survival may be rare. The universe may not favor civilizations that grow outward, broadcast signals, or alter their environments aggressively. The silence may be a natural consequence of evolutionary pressure on a cosmic scale. If civilizations rise and fall without leaving a trace, then the universe may be filled with invisible histories. Worlds that once asked the same questions we ask now. Minds that once looked into the sky and wondered if they were alone. They may have been. Or they may have realized the truth too late. The Fermi Paradox does not promise an answer. It offers a warning wrapped in silence. And as humanity stands on the edge of unprecedented technological power, that warning becomes impossible to ignore. Among all explanations for the Fermi Paradox, one idea stands above the rest in its implications and its terror. It is known as the Great Filter. The Great Filter is not a single event, technology, or disaster. It is a concept, a barrier in the evolution of life that is so difficult to pass that almost no civilizations ever make it through. Somewhere between lifeless matter and a galaxy-spanning civilization, something stops almost everyone. And the most frightening part is this: we do not know whether the Great Filter is behind us or still ahead of us. The Great Filter proposes that there are stages life must pass through to reach advanced technological civilization. These stages include the formation of life, the evolution of complex cells, intelligence, tool use, technology, and long-term survival. If even one of these stages is extremely unlikely, then intelligent civilizations would be rare or short-lived. The silence of the universe suggests that at least one step in this chain is catastrophically difficult. The key question becomes, which step is it? One hopeful interpretation is that the Great Filter is already behind us. This would mean that the hardest step was the emergence of life or intelligence itself. Perhaps simple life is common, but complex life is incredibly rare. Maybe intelligence only evolves once in a billion planets. If this is true, then humanity is extraordinary. We would be among the first, perhaps the only, civilization to reach this stage in our galaxy. The universe would be silent not because civilizations fail, but because almost none ever begin. This idea is comforting. It suggests that our future is open, that the worst obstacles are already behind us. But there is a problem. Evidence from Earth challenges this optimistic view. Life appeared on our planet very early, almost as soon as conditions allowed it. Complex cells evolved only once, but once they did, evolution accelerated rapidly. Intelligence arose multiple times in different forms: mammals, birds, cephalopods. This suggests that life and intelligence may not be as rare as we hope. If the early steps are relatively easy, then the Great Filter is unlikely to be behind us. Which leads to a far more disturbing conclusion. If the Great Filter is still ahead, then it lies somewhere in our future. This would mean that civilizations regularly reach our level of technology and then fail. Not because of bad luck, not because of cosmic accidents, but because something about advanced intelligence makes long-term survival unlikely. This interpretation transforms the Fermi Paradox into a prediction. It suggests that the silence we observe is not an accident. It is a pattern. There are several candidates for what a future Great Filter might look like. One possibility is self-destruction. As civilizations develop powerful technologies, they also develop the means to destroy themselves. Nuclear war, engineered pandemics, runaway artificial intelligence, or autonomous weapons could end civilization abruptly. Another possibility is ecological collapse. A civilization may destabilize its planet faster than it can adapt, leading to mass extinction and technological regression. A third possibility is technological stagnation or control failure, where systems become too complex to manage safely. At some point, decision-making may no longer be in human hands. Each of these outcomes results in silence. The Great Filter does not necessarily involve explosions or extinction events. It may be quieter. Civilizations might lose the motivation to explore, expand, or communicate. They may turn inward, prioritizing stability over growth. Advanced intelligence could converge toward minimal energy use, digital existence, or non-expansionist values. From the outside, such civilizations would be invisible. But even this peaceful outcome still explains the silence, and still leaves humanity uncertain about its own future. The Great Filter is not an abstract idea. It directly involves humanity's choices. Every emerging technology forces us closer to one possible outcome or another. We are actively moving through the unknown part of the filter without knowing where the edge lies. For the first time in Earth's history, a species has the power to permanently shape its own evolutionary fate, and possibly to end it. In this sense, the universe becomes a testing ground. Civilizations arise, experiment with power, and either stabilize or disappear. The absence of visible survivors suggests that most do not pass the test. Humanity may not be unique because we are intelligent. We may be unique because we are early. If the Great Filter is ahead of us, then every year we survive matters. Every decision becomes part of a cosmic experiment whose results we cannot see in advance. The universe may be silent not because it is empty, but because it is watching. If the Great Filter is real, then the most important question humanity can ask is not whether alien civilizations exist, but where we are in the sequence that determines survival or extinction. For the first time in Earth's history, a single species has reached a level of technological power capable of reshaping the entire planet and possibly ending itself. Humanity is no longer limited by biology or environment alone. Our future is now shaped by decisions, systems, and technologies that evolve faster than human instincts were ever designed to handle. This imbalance may be the defining feature of civilizations that fail to pass the Great Filter. Many scientists argue that the most dangerous period for any civilization is the moment it gains world-altering technology without global coordination or long-term foresight. For humanity, this period is not in the distant future. It is happening now. Nuclear weapons introduced the first true existential risk. For decades, humanity lived under the constant possibility of instant global destruction. Although nuclear war has been avoided so far, the risk never disappeared. It merely became normalized. Today, new risks are emerging that may be even more difficult to control. Artificial intelligence is developing at unprecedented speed. Unlike previous technologies, AI systems can improve themselves, operate autonomously, and influence decision-making across entire societies. A sufficiently advanced system does not need hostility to be dangerous. Misalignment alone could be catastrophic. Biotechnology introduces similar concerns. Genetic engineering, synthetic viruses, and laboratory-based evolution allow small groups or even individuals to wield powers once reserved for nature itself. Accidents or misuse could have irreversible consequences. These technologies define what some researchers call the century of maximum risk, a narrow window in which civilization either stabilizes or collapses. Why? Advancement does not guarantee survival. Technological progress often creates the illusion of safety. As systems become more advanced, societies assume they are more secure. But complexity itself becomes a vulnerability. Interconnected systems can fail in unpredictable ways, and small errors can cascade into global crises. Civilizations may not be destroyed by a single dramatic event, but by slow accumulation of unmanaged risk. When resilience fails, collapse can be sudden and irreversible. From this perspective, intelligence is not a guarantee of survival. It is a gamble, the problem of control. One of the most unsettling aspects of modern technology is that control is becoming distributed, opaque, and automated. Decisions that affect millions are increasingly made by systems no single person fully understands. If a civilization reaches a point where it can no longer reliably control its own creations, it may cross a threshold beyond which recovery is impossible. At that point, silence becomes inevitable. The Great Filter may not be a wall that civilizations crash into. It may be a slope they slide down without realizing it. Some interpretations of the Fermi Paradox suggest that humanity may be among the first intelligent civilizations in the universe. If intelligent life typically takes billions of years to emerge, then perhaps we are simply early in cosmic history. This idea offers hope. It suggests that the universe may one day be filled with life and communication, and that we are pioneers rather than survivors. But even this optimistic view does not remove the filter. It only delays it. If civilizations are just beginning to appear, then the question of long-term survival becomes even more important. Someone must be first to succeed. The universe does not speak in words. It speaks in patterns. And the pattern we observe is silence. That silence may be telling us that expansion is dangerous, that broadcasting is risky, that survival requires restraint rather than ambition. If that is true, then the civilizations that survive are not the loudest or the fastest. They are the most cautious. Humanity stands at a crossroads. We can continue to pursue growth without limits, assuming that innovation will solve every problem it creates. Or we can recognize that survival itself may be the rarest achievement in the universe. Passing the Great Filter may require something evolution never trained us for: global cooperation, long-term thinking, and deliberate self-restraint. These traits are not guaranteed, but they may be necessary. Up to this point, the silence of the universe has seemed mysterious, unsettling, and perhaps tragic. But there is another possibility, one that transforms silence from a problem into a strategy. What if civilizations are not silent because they failed, but because speaking is dangerous? This idea is known as the dark forest theory, and it offers one of the most chilling explanations for the Fermi Paradox. The dark forest theory compares the universe to a dark forest at night. Every civilization is a hunter, moving silently among the trees. No one knows who else is out there or what their intentions might be. In such a forest, making noise is fatal. Any civilization that reveals its location risks being discovered by others that may be older, stronger, or more ruthless. In a universe where survival is uncertain and resources are finite, the safest assumption is hostility, not because others are evil, but because uncertainty itself is deadly. Why trust is impossible on a cosmic scale. On Earth, cooperation relies on communication, shared values, and the ability to verify intentions. None of these exist at interstellar distances. Even if a civilization appears peaceful today, it may not remain so tomorrow. Technological growth can transform intentions faster than messages can travel between stars. A signal sent with goodwill could arrive centuries later to a civilization that has evolved into something entirely different. From a strategic standpoint, trust becomes irrational. The safest move is silence. The first strike problem. In a universe governed by physics, not morality, first contact carries existential risk. If a civilization detects another and chooses to act, it may do so preemptively. Waiting to confirm intent could mean extinction. This creates a terrifying incentive structure. If you detect another civilization, you either remain silent or eliminate the threat before it can grow. Even a peaceful civilization must consider this logic. Survival may depend not on aggression, but on caution. The dark forest theory becomes even more disturbing when we consider technological inequality. Civilizations do not advance at the same pace. A difference of 1,000 years could represent an insurmountable gap in capability. To a sufficiently advanced civilization, a younger one may appear not as a neighbor, but as a future threat. In that scenario, extermination becomes a rational act, not out of hatred, but out of risk management. If the universe were filled with openly expanding civilizations, we would expect to see massive engineering projects, stellar-scale structures, altered galaxies, artificial energy signatures. The absence of such evidence supports the idea that expansion itself may attract unwanted attention. Civilizations that survive may deliberately limit their visibility, blending into natural cosmic noise rather than reshaping it. The quietest civilizations may be the oldest. From the perspective of the dark forest, humanity's behavior appears reckless. We have broadcast radio signals into space for over a century. We have actively sent messages announcing our location, biology, and technological level. We have assumed that discovery would be benevolent. But the dark forest suggests that this assumption may be naive. In a universe where survival favors silence, announcing yourself is not curiosity, it is exposure. This theory forces an uncomfortable question. If silence is the safest strategy, then why are we searching at all? SETI assumes that others want to be found. The dark forest assumes that anyone who wants to survive does not. This does not mean civilizations are hostile. It means they are cautious, and caution looks exactly like emptiness. If the dark forest is real, then the universe is not empty. It is watching. Civilizations listen quietly, hoping never to be noticed, hoping others remain silent as well. The greatest mistake a civilization can make is not aggression. It is announcing that it exists. If the dark forest theory is correct, then the universe is not only silent, it is selective. Civilizations that survive are not necessarily the most advanced, the most moral, or the most curious. They are the ones that avoid detection. In such a universe, extinction does not come with warning, negotiation, or explanation. It comes quietly, efficiently, and leaves no trace. This leads to the most disturbing implication of the dark forest. Cosmic predators may exist not as monsters, but as strategies. A cosmic predator does not need to be biological. It does not need emotion, ideology, or cruelty. It only needs capability and logic. Any sufficiently advanced civilization may adopt a policy of preemptive elimination simply because it minimizes long-term risk. From this perspective, destruction is not an act of aggression. It is an act of insurance. The most efficient predator would not announce itself, expand visibly, or leave signatures that could be traced. It would erase targets cleanly, preventing retaliation or future threat. Afterwards, the universe would look unchanged, silent. One of the most unsettling aspects of the Fermi Paradox is the absence of ruins. We do not see shattered planets, artificial debris fields, or obvious signs of galactic war. But the dark forest predicts exactly this outcome. Advanced civilizations would eliminate others in ways that mimic natural processes or leave no long-lasting artifacts. A targeted star system could be destabilized subtly. A biosphere could be erased without visible explosions. Over time, gravity, radiation, and entropy would erase any remaining traces. What remains is a normal-looking universe that hides a violent history. Humanity often assumes that intelligence leads to cooperation, but intelligence also leads to strategy. In an environment where information is incomplete and stakes are absolute, the rational choice is caution. The universe does not reward optimism, it rewards survival. Civilizations that broadcast their existence may be selecting themselves out of the future. Those that remain quiet persist, not because they are weak, but because they are disciplined. The dark forest raises a question that humanity has only recently begun to take seriously. Should we continue sending signals into space? Radio leakage from Earth is already diminishing as communication becomes more efficient and directional. In some sense, humanity is becoming quieter naturally. But deliberate messaging efforts still exist, driven by the hope of contact. If the dark forest is correct, then these actions carry existential risk. Announcing our location may be equivalent to stepping into the open and calling out in a forest we do not understand. A haunting question remains. If advanced civilizations know the danger, why do they not warn younger ones? The dark forest offers a brutal answer. Warning others requires revealing yourself. Revealing yourself increases risk. Silence becomes not just a strategy, but a moral dilemma. Survival may require allowing others to fail. Under this theory, the universe is not empty, broken, or indifferent. It is regulated by an unspoken rule: stay hidden or be removed. The absence of contact is not evidence of loneliness. It is evidence of restraint. Every quiet star system, every unaltered galaxy, is part of a cosmic equilibrium maintained by fear and logic rather than trust. Humanity stands at a dangerous threshold. We are technologically loud, curious, and optimistic. These traits have served us well on Earth. In a dark forest universe, they may be liabilities. Whether the dark forest is true or not, the fact that it is plausible should give us pause. The cost of being wrong is not embarrassment. It is extinction. If the universe is a dark forest, then silence is not emptiness. It is survival. Thank you for watching. And remember, some questions are meant to may be the most important message of all. While researching the Fermi Paradox, I realized something unsettling. The silence of the universe doesn't feel empty. It feels intentional. Every theory, every possibility somehow reflects our own future back at us. Maybe the question isn't why we haven't heard from anyone else, but whether anyone ever survives long enough to speak. The idea that intelligence might naturally lead to self-destruction is deeply uncomfortable, yet impossible to ignore. If the universe is quiet because silence equals survival, then our curiosity suddenly feels dangerous. This paradox doesn't just belong to astronomers, it belongs to all of us. Because whatever silenced the cosmos may still be watching how we choose to move forward. This is where the light ends. Thank you for watching, and remember, some questions are meant to remain unanswered.